Good day, stat students. So we're going to talk about our final lecture of the semester, chapter 12. And what we're going to do is we're going to eventually introduce inferential statistics with regards to regression analysis. But before we do that, we want to review regression and correlation. And so remember, with regression and correlation, we're taking a look at the association between two quantitative variables. So, since we have two quantitative variables, we got to figure out which one's the response and which one's the explanatory. So the response, that's the one that we're trying to figure out why it's changing from person to person or thing to thing. That's given the y. Explanatory does the explaining, and that gets the x. Okay, let me get my pen out. X, the explanatory, right? The explanatory. Okay. So we took a look at a city's latitude and average January temperature. Since this is a review, I'm going kind of quick through this, okay? When we get to new stuff, I'll slow it down, okay? So which one was the y and which one is the x? Latitude is the explanatory. It does the explaining. It explains why the average January temperature is what it is for a city. So the average January temperature is y. Here was our data for our 10 cities. Okay, and we took a look at a scatter plot. So you should remember that a scatter plot is used to look at the comparison of two quantitative variables graphically. So here's our scatter plot that we're going to make. Here's Miami, there's Mobile, there's Lincoln, Nebraska, and then there's the rest of them. And we had a relationship that looked like that. And notice that the slope here is negative. That means we have a negative relationship. As x increases, y tends to decrease. So as latitude increases, average January temperature tends to decrease. But we could also have a positive relationship. So the slope is positive. So as x increases, y tends to also increase. So like height and weight. Or how about study hours and score on an exam? Then we could have no relationship. So our sample regression line would go straight across like that. And we get the big blob of nothing. We could also have a relationship that's curved. So if you took a look at latitude and average January temperature from, I think it was a city, I think I started with Canada and went all the way down to the South Pole, that we have this curved line here. All right, that's actually representing latitude and average January temperature. Okay, we have two graphs here, and both of them have a negative slope to them. All right, both has a negative slope. Okay, but this one clearly is stronger than this one. Why? These dots are much closer to the line than these dots over here. So slope by itself can't say how strong that relationship, it just can tell us if it's a negative or positive, right? And so we got to have something else that tells us how strong the relationship that we have between two variables, and that's where the correlation coefficient comes into play. So let's review about the correlation coefficient. The symbol for it is R, and it's a value from a -1 to a +1. The sign of R indicates the type of relationship. So a negative R indicates what? A negative relationship. A positive R indicates a positive relationship. So if you have an R that is close to a -1, say a -0.89, -0.94, that's indicating a strong negative relationship. An R that is close to a +1 indicates a strong positive relationship. So if you had 0.81, 0.96, right, something like that, strong positive relationship. And anything that's close to 0, we're saying that that's indicating no relationship, okay, or at least a very weak one, right? So you can review those last two lines. That's just telling you if we have moderate, weak, or what have you. Okay, so you can take a look at those. And then slope and the correlation will have the same sign, but it would be very unusual for them to have the same value. All right, So let's take a look at some values for r. So if you had an r of a -1, you have a perfect negative relationship, and all the dots are right on the line. Okay, and we have a negative slope to our sample regression line. Perfect positive, all the dots are on the line, slope is positive, all right, and here r would be a +1. No relationship, or close to it anyways. We have an r that's going to be close to 0, okay, and like if we took a look at GPA and height, GPA has nothing to do with a person's height, okay, and we would see no relationship there. Big blob of nothing. Okay, let's take a look. I already have the line drawn here, so let's take a look. So we have a line drawn here. It looks like a positive relationship. Relationship looks pretty strong. The dots are pretty close to the line, right? Let's take a look at the correlation. Correlation is 0.89. Pretty strong. Positive relationship. Here we have a negative relationship. Notice we have a dot that's getting really far away from the line. So this is getting pretty spread out. I would say this is a relatively weak negative relationship. And we see that here with the correlation, -0.29. Here we have a strong positive relationship. I mean, there's hardly any variation off the line. And so this turned out to be a correlation of 0.99. Then we have a weak negative relationship. We have a few dots that are getting kind of far away here, here, and here. Okay, and so, but it's not that far away. So they're not as spread out as that last -1. So I would say this is moderately strong negative. So that's what we see with the correlation here, -0.66. All right, let's take a look at this one. Let's see here. I haven't drawn the line yet. So it looks like we have a negative relationship. So we can already eliminate, looks like 2 of these, right? We can eliminate this one as far as the value of the correlation coefficient, and then we can eliminate this one because that's not even a valid value for the correlation. So what would a -0.05 look like? Well, the dots would have to be what? A lot more spread out and hardly seeing any type of relationship between the two variables. Certainly we have a relationship here. I would say that when we take a look at the correlation, it's going to be close to a -0.88. And that's what it is. Okay, so a little review with correlation. So you'll see that on the comprehensive part of the final. Alright, so I wanted to remind you of something here. So here we have no relationship. Okay, and what I would want to remind you here is that the slope of the sample regression line, what would be the slope here? The slope would be equal to, now I don't know if it's exactly 0, but we're going to pretend that it's 0. That when you have no relationship, the slope of the sample regression line will be 0. This is one of those strange times that if you had truly no relationship between two variables, that the slope and the correlation would be exactly the same value. It would be 0. Okay, and so I just want to remind you, because this is going to play a part of what we're going to talk about next. Okay, when we get into the inferential statistics, we got to remember that no relationship means slope is equal to 0. All right. So now what we have to realize is that it says here slope of the population regression line. Remember, when you do inferential statistics, you don't do it on samples, you do it on the entire population. You test parameters, and so we're going to be testing the slope of the population regression line. So with our example with our cities, we're going to pretend that we took all the cities in, say, the U.S. continental 48 states, and we put all the cities and all their average January temperatures into a model, and we went ahead and drew this the population regression line. Okay, and so what we're testing is the slope of that line, putting all the cities and all their average January temperatures into a scatter plot and figuring out what the slope would be. Okay. So if the slope of the population regression line is equal to 0, that means there's no relationship between x and y. So we have what's called the slope test. slope test. You need to remember that slope test. So the slope test is the following, is that we're going to test whether the population regression line is equal to 0 or not. And so there's no debating it. This is pretty much the standard for the slope test, is that we go ahead and test if the population slope is equal to 0 versus HA where the population slope is not equal to 0. It's pretty much the standard. Okay. StatCrunch allows you to change some things around if you wanted to, but trust me, this is always going to be the default on every computer program unless you specifically go in there and want to test something else. Okay, so let's go ahead and take a look at the computer program for computer output for StatCrunch, because every time a regression analysis is run on the computer, it will provide the slope test. You just need to know what to look for. So here's our data, and I put it into StatCrunch. And if you go to Stat, regression is simple linear, and then put in latitude and average January temperature for X and Y. Notice down here, okay, notice it says hypothesis test. And so notice the default. Slope is equal to 0, slope is not equal to 0. Okay, you hit compute, and this is the output that's given to you. Now, before we concentrated on this stuff up here, what I want to concentrate on is now this stuff down here. Okay, so once you start seeing things like t-stat or test statistic and p-value and things like that, we're talking about a hypothesis test, right? And two hypothesis tests are being tested here. Now, I guarantee you, for every computer program that's doing regression analysis, that the first line will always be about testing if the y-intercept is equal to 0. And that's not what we want to take a look at. That's not the slope test. Okay, it's rare that we even take a look at that test, to be honest with you. What we want to take a look at is this guy down here. It's always going to be the second line. Always going to be the second line. Okay, and I just want to kind of warn you that not every computer program uses the word intercept and slope. Believe it or not, they use different language there, but I guarantee you that the slope test will always be the second one, will always be the bottom one. Okay, and that's the one that we want to take a look at. So notice that this is just the value of the slope right there. Okay, and standard error, that's kind of an ugly thing to calculate. Thank goodness we're allowing the computer to calculate that one for us. That's kind of a pain to do by hand. There's our degrees of freedom. There's the test statistic. And really the thing that you want to take a look at closely is that value right there, that p-value, because it's the p-value for the slope test. If the slope test, if the slope, population slope, is equal to 0 or not, that's what we want to take a look at. Okay, so in other words, the p-value is very, very small for this particular regression analysis. All right, so usually we go ahead and set the significance level to 0.05, and so alpha is going to be set to always 0.05. I have never seen it pretty much anything else. Okay, so we're going to run the slope test at 0.05, and so if the p-value is technically is less than or equal to alpha, we'll go ahead and reject the null. All right, so if it's less than 0.05, we'll reject the null. So let's see here. Our p-value is really, really small. That's less than alpha. So we're going to reject the null. We have strong evidence that the slope of the population regression line is not equal to 0. Okay, fine, because we rejected this and we thought this. Okay, but what does that mean? Well, remember what this means. This means that there's no relationship. Okay, and over here it means that there is a significant linear relationship, and that, what is that telling us? Is that x could be reasonable to use to predict values for y. Alright, so that's telling us that x and y are linear related. Okay, there's some sort of significant relationship between there because the population slope is not going to be equal to 0. So x could possibly be a decent predictor of y. Okay, now here's the thing, is that the slope test is giving us an idea if x is a reasonable predictor of y, and that x and y are significantly linearly related. Okay. However, we might look at it and say, let's see, okay, fine, the slope can't be equal to 0, but let's take a look at r. And maybe r is only like, the correlation coefficient is only, say, like 0.2. Okay, you're going, hold on, okay, so the slope can't be equal to 0, but this correlation is really low. Okay, and so what that's telling me is that, okay, we can still improve upon our model. Okay, that our model's not significantly strong enough maybe to do a great job in predicting values for y. Okay, and we maybe have to add more variables to our model. Okay, so the last thing that we should talk about in this course is r squared, the coefficient of determination, but normally it's just referred to r squared. Okay, but that's the official name that's given. So r squared is a value that goes from 0 to 1, but many programs it shows it as a percentage. Okay, and so a lot of programs will show it from 0% to 100%, and it's the percentage of variation in y that is explained by x being in the model. So do we want to? So think of y. Y is changing from city to city, right? And so we have a lot of variations because we had Miami that is in the mid 60s, and we have Duluth, Minnesota that's in the mid, it's like 5 or something, or 7 or something like that, right? So we have a decent amount of variation in average generating temperature. Okay, do we want to explain a little bit of that variation or a lot? And we want to explain a lot, and that's what r squared is telling us. How much of the variation is explained by our model? Okay, and so r squared, notice, so there's the correlation coefficient, and right below it is r squared. Now, StatCrunch puts it as a decimal, but really we should probably think of this as 96.54%. Very close to 100. So what this is telling us is that 96.5% of the variation in y is explained by x, the city's latitude. So the slope test is significant. R is pretty high. It's a very strong correlation. R squared is very high. This is telling us that our model is really good at predicting values of y going forward. And we saw that with, Nashville, back in chapter 3, that we saw that Nashville, we were able to predict Nashville's average generating temperature within a degree or two. That's pretty darn good. Okay, and so that's what the inferential statistics is all leading to. Do we have a good model to help us predict values of y or not? And so if the slope test is not significant, if the p-value is greater than 0.05, that automatically is telling us that we don't have a very good model. Okay, but even if the slope test is significant, we still have to look at r and r squared. Okay, and if r and r squared are both low, well, maybe we need to improve upon our model a little bit. Okay, and so I just kind of finished things up here. So we would prefer value for r squared that's closer to 100%, right? That's telling us that the model is good at predicting values of y for a given x. So you can't just look at one of these by itself. You want to look at all of them together, okay? And start asking yourself, hey, would this model be good at predicting values of y? Okay, r squared, slope test. Okay, so that ends the course. Thank you for your time.